So Archimedean property, the Archimedean property for real numbers. Okay, so I used to know what it meant was, I think it tells us that the real numbers go forever to the right.
Yeah, proof for that? It's on the definition? Oh no.
I think that's what this thing says. I'm not sure. Let's see what it says. If alpha and beta
Rational numbers, because they're great.
real
Numbers, because they're great.
not only that, but they're really very cheery, positive real numbers. Two positive real numbers. So since these are Greek letters, which means Q. Yeah. Now I'm going to do two things, and then we're going to know. Let's just do. Okay. Which one is going to be alpha? Which one is going to be beta?
Alpha begin.
Yeah, alpha's the left to right.
So here's the problem. The next theorem that I got lost in is the density of rational numbers. So they built a rational number between two reals. They said alpha was less than beta in the statement of the theorem. And here they don't even give it to us. So I'm just going to write another line here. This is the line we need. Is there something missing here?
Zero. Zero.
Genius child. You approve? So this is the disapprove section on the right hand side. And then the statement goes, then there is some our favorite word is going to show up again, so I'm going to underline positive. Because if this number was negative, things would go to the left. Positive integer. So positive integer means it cannot be.
Can't be real. It's not a number at all. It's
Can't be rational. Can't be rational.
We're not talking about, we just talking about integers.
Yeah, it's natural number. It's a natural number.
Very good. Very good.
Okay.
Why didn't they just?
Number not being okay.
Because it doesn't have a zero. Natural numbers are positive integers because they are 1, 2, 3 forever. There is no zero here. No zero. I would have said there is some natural number, but they did this. So zero is not involved. And that
just put zero.
So this n can only be 1, 2, 3, 4. Okay. Such that and here is our condition such that if we take this positive integer and multiply, take that positive integer n and multiply it into, let's say, alpha, then it's going to be greater than beta. Oh.
It has to be greater than 1.
Okay, so 1 is out, 2 might work. 2 might work if we put numbers in here, which is what I did for the other proof, and then it started to make sense, but we're going to remove these as soon as we're done. So we could take 100 here, multiply 100. Sorry, my colors are off. So if we did 100, we pick 100, multiply it into this guy. It is going to be, if beta is 2, it's going to be over there. Even when alpha is 1.
Yeah, it's going to bring alpha
This product is going to be bigger. It's a product. It's going to be bigger than that real number.
And alpha B1, yeah, alpha can be B1, it can be a real number that's from a subset.
Okay. Plus, what is this thing? The product itself is a real.
Yep.
So, yeah. So, and so what we are finding is we are finding real numbers to the right when we multiply an integer predicate. So yeah, antecedent, consequent, or these are the things that we assume, the conditions, and this is what we, this is also an assumption. This is what we have to show. So there are three conditions. No, there are two basically. There are two real numbers, alpha and beta, and then there is an n, positive integer. If you take n and multiply one of them, the product will be bigger than the other one. That's why the order doesn't matter, right? I should say that. So, yeah, if we, yeah, it doesn't matter which one you, they just want, this is kind of like, this is the, I guess, speaking of, this is the, what is it in this horses jump over? The fence. This is the, is it really the fence?
It's the frog. You ever played like leapfrog?
Yeah. So this is a fence, and this fence kind of gives us the sense that this thing, after getting multiplied, jumped over that. And therefore, this, we don't need this.
A and B are meaningless.
Yeah. Yeah. And the order does matter. We want one of them. We could have multiplied here, but then it wouldn't be jumping over something. This has to be bigger than this in order for this product to be bigger than this. That means it's moved to the right. Okay, let's do the proof.
Okay,
Yeah,
so
yeah. Oh, beta both greater than 0,
It is 0.
greater than 0, and then we have and because we're representing, these are real numbers because they're in Greek, and then comma, what's the other thing? N is also greater than 0.
N greater than 1. Doesn't work times 1.
No, it has to be just positive. This doesn't work. Sum tells you that you can move on from one to the next one. Again, he's very good intuitively. If you were writing this proof, you would have done that. Yeah, but I think it's easier to say that this by adding. So if you take this out, then this is what.
Yeah. So it's the same thing, but written off.
Yeah, and this is more generalized version. Maybe I don't. This is more elegant than. I think this is fine too. Yeah, because there are lots of proofs that uses 1. 0 and 1s are fine to use. So I would go with what you're saying, and that's fine too. Because you find another book, it will be the same property will be stated differently. So now I'm doing this. I'm giving you the what is the formalization of the theorem here. Alpha and beta are greater than 0, comma n a positive integer. So I can also write here, but we know this sitting here. It's a or n.
oh yeah.
Yeah, I'm going with you or. Or positive integer implies that if we multiply n,
we need the alpha and beta, which is like a set of real numbers. They are within the set of real numbers.
He said because they're a Greek letter.
the Greek letters. So we're going with that. And then that's why we don't even have to do this.
I mean, it works. If we like set it here.
For chapter 1, it works. Otherwise, you would have to throw that in. Of course, this is a shorthand, right?
Yeah.
And this is just me. I've invented this. So I don't know if this is the. Okay, so this is your. So now you guys are going to do the proof. Let's see how far we get this time. This is simpler, so it will be faster.
Yeah, it feels separate.
Hopefully, but you never know.
Can't use any accent.
Okay, so first step in a proof is
Draw a picture.
no, or yes, but also elaborate. Because all we had was if there the proof went if there is alpha and beta that are positive real numbers, then there is some n positive integer n such that if you multiply n into one of those alpha or beta, the product will be bigger than the other one. To the right, yeah.
I have a
Hmm.
simple question.
Yes, sir.
We state what we're trying to prove first, which is what you just did. State our conclusion or our.
Oh, no.
Sorry, I told you.
So we're going to
Hmm.
assume the opposite.
Yes, brilliant. So suppose, so we're going to choose one of these things, right?
So are you going to choose the,
Yes.
the predicate or the antecedent? The
Consequent,
consequent.
and then this is antecedent, but you're right, your terms are also correct. So what we're going to do is,
One of those two,
we're going to, yeah, so I think in this case, yes, and the reason for that is this has everything in here. We just, if we assume this will lead us to a contradiction. If we assume the opposite of this, because this is true, we know the theorem works. We know that, so yeah, what we're doing is trying to figure out what's the reasoning going on. You went to that, and now I'm trying to think about, this is complex enough to start off, even if it was a direct proof, right? Laying this out is not going to get us much. Even in a direct proof, I would have just gone straight here and unfolded it and see where it takes me. And then as I'm unfolding it, I would then bring in the assumptions.
So are we doing contradiction because they gave us the theorem to begin with, and we're just trying to see if we can break it?
No, there might be a direct proof for this, but contradiction proofs are, so I don't have the intuitive sense of it, but I've seen two proofs where one was done by contradiction and one direct. They both worked, and this might be easier to do. And so you're gonna say,
Alpha
yeah.
is actually less than. Right?
So we're gonna go, suppose, no, we're gonna just switch this out, right? We're gonna take the opposite of that. Suppose that for all n, and then give me the opposite of that.
I think it's what you were saying, n times alpha is less than beta, and let's go with the inverse function. But
There is no n that can use b, or is it going to be?
What this is saying is that every time you get a product, it will be on the, it won't jump over. Yeah, so it won't jump over the fence, but will get stuck behind it. See, now we have the image in our heads. That's pretty cool. So so I'm going to draw a little picture here just to remind us the true situation, which is alpha, beta, and then 0 here. And we don't have to show n, but I mean, we could. Let's put n here just for the hell of it. And then this is another real number. Okay, so because if you multiply a real number with an integer, it still remains a real number. I think for some reason I know that because I'm blessed. Yeah. Where does
In alpha is going to be less than.
and it's not equal to, it's less than, right?
Yeah.
Where,
Times alpha plus below.
and before or after?
I don't think it matters, but
Very good.
I'm going to say after alpha.
Yeah. And again, this is
that's a proof for one.
all the products. If we assume this to be true, right? We are assuming this to be true right now. Assuming it to be true for sake of contradiction, then all of them would fall here and we would get a set.
Yeah. Oh, we've created another set.
With,
where the
yeah,
lowest bound is 1 alpha and the upper bound is,
this guy's picking up, exactly. And this is your LUV.
and that LUV would be, you have to kind of like.
And
solve
it
by-
can be equal to this thing, right?
You have to say N alpha equals B, so then alpha,
Forgot about this.
so then N. B over N equals alpha, is kind of what that is.
Ah, oh yeah, okay, so keep your thoughts. Let's create the set. Then, so the set is going to be A. They're going to the set. Why are they going to the set? Anybody? Definition.
Both sets.
Or if this is going to be an LUB, what we're going to do is what the proof is doing is throwing shit at it. And some of the things are going to stick and take us to the right place, and some don't. So you throw all the definitions. You know, this is how you do the proofs. You throw all the definitions, and if you've done enough of these, you know intuitively where to go in the exams. It is. Otherwise, nobody would pass those classes. Okay, so once you've done enough of these things, you know. So what they're throwing at us is they're creating the set N, a set that contains all of this. Because sets are when we deal with, think of this, what you just said, this seems like an upper bound. It just doesn't jump over this.
Yep.
Once this condition is assumed true, it forms a barrier. We are on a queue. This is logically an LUB.
And then we have a GLB at, actually, this is true.
Yeah, we don't, that is our GLB kind of.
But since.
But
N
if
is a non-zero integer,
GLB, sorry,
it's just the lower bound, it's like, and then our set is.
because they only take, because they don't, they only take this out.
Then 1 is the lowest that N.
In fact, one is the only integer. We're not dealing with fractions.
Yeah.
One just keeps, okay, you're right. So one keeps bringing you back to this guy. So that's fine. And this is included then, right? Alpha is included. Yes, alpha is. So our set A contains alpha, everything, all the N alphas, and then our LUB, our beta, and this is our set.
We could create another set for the values of N.
Yeah. So that is called we don't call it a set, we go, you can just say it like that. I've seen it.
And then 1, 2, 3, and then your least upper bound would be beta divided by alpha.
Your least upper bound for which one? This set or this? This is not a set we have to worry about. The least upper bound is beta.
Yep, and then for N, the highest number it can be is, in this instance.
Is infinity, dude. Is N.
Nope.
What?
Because it's the set of N's for, it's like the possible N's for the set.
N is not a set. We're not looking at N as a set. The only
N doesn't need to be like below A. Or
No,
alpha. It can
no.
be above A or above B.
Uh,
It doesn't matter.
the only condition that we need for N is that N is not equal to 0.
Okay.
Okay. N then can only be equal to 1. If it is 1, then when we multiply 1 into alpha, we are still here.
Would it help if we wrote alpha is n times alpha and b is n times alpha too? Does it matter? Because they're all technically.
So this,
n times alpha, right?
no, okay, what happens is as we populate the set with N, with the product N times alpha, we are going, as we go up, right? 1 gets us here, 2 gets us. Let's say this is 2. This is a finite set of. Oh, that's the other thing I'm noticing now. It's a finite set of real numbers.
Yeah.
Yeah, because it's a finite. That's where you were going. That's what you were talking about.
You asked the question, then why is it a set?
Who?
You.
No. This isn't a set because it's an int. So what happens is this, let's say this is 3, right? This is 3. And depends on how long this is, right? Beta could have been all the way over there, right? But there will be an this will be the last one in our decoration. It will be this. If we start using, let's say I put 2 here, I put 3 here, then I put dot, dot, dot. The last one will equal beta, potentially, or not, because it says less than, right? Depends on where beta is sitting. It might not hit it. It can be equal to, that's fine. It better be less than, and it always is. Okay, so now we go. Then the set A equals, what's the definition of this set? What does A consist of? Products? We wait for our, sir?
I just did something very backward.
Okay, so then the set A equals what? Products, right? So what do I put in here? What's the, like, if it was a,
Alpha and alpha and beta.
so I do this such that, what's the condition?
It's within the set alpha beta.
So we write this again. As long as the product of n and the real number alpha is less than or equal to beta, it is a member of this set,
Oh, okay.
right? Or they didn't even go that far. I don't like this, but they did this. I think this is better. This is just a, so they said this is enough to define the set.
Yeah, because beta could be anyone.
Yeah, okay. Is, now is the cool thing, is bounded. This is where this definition comes in here. This condition then becomes, is bounded above by beta. Is that true? Yes. All the elements, all of these are less than or equal to beta. Elements of, so the set A is bounded by this because all its elements is less than or equal to beta. So we're just using definitions. Next we go, we still haven't got to the contradiction. Okay. Oh no, okay, so we just got to the, contradiction, we need to go to the LUB, right? So we threw this on it. We have found an upper bound by doing this, because before, what does this say? The actual proof says no upper bound exists. Oh, that's what it is. Okay, so the theorem says there is no upper bound for the products, for this product.
Oh,
If we switch, which we just did, by switching, so this is what's really happening. Once we switch the condition, we found an upper bound. If we found an upper bound and the set is not empty, that's why they defined it. This is non-empty. Sorry, this and null set. And we found an upper bound. These two conditions mean that LUB exists. So let's stick in the LUB, and then we're going to just do algebra and prove that our LUB makes no sense. Therefore, this condition is wrong and the theorem is true.
all right, are we gonna set our LUB to be beta?
Let's see what they do. It says LUB,
Oh, no, yeah, that's gonna be beta.
it's going to be beta.
Not great, it's low bound.
It has to be, because we didn't find the upper bound that we found is right there, the last thing in the set. Okay. So there is, it says there is an upper, there is a least LUB for A, and then it says, which we will call lambda. They had to drop the damn thing. So, okay, which means, all right, then this is when I just assumed, yeah. And this is again, since I don't really know math, but I have a weird relationship. I assumed that just like the discussion, the class discussion here and you, that this is our lambda, this is our LUB. So I put it in the diagram and the rest of the thing makes sense. And so then I'm like going, my choice is correct. So that the upper bound is the LUB in this case, which is very evident if you have Q here, and because the upper bound is not sitting here. It's this one. There is nothing sitting here. Okay, so there is no upper bound sitting here. This is the rightmost real number, and it has to be the least upper bound. I mean, there are numbers that are bigger than that, right? Yeah. So, but our upper bound is the least upper bound. To finish this today, okay. So we have the lambda.
That's when you know the conversation starts getting.
We have we have alpha, and we have a one little dude here, and alpha, and then. Okay, and I just need to make this. Yeah, that just looks kind of cool. I mean, it does look cool. Okay, all right, so we are ready. We can drop the beta business now. Okay, so, and it turned out the rest of the proof works if you have this picture where R beta became the least upper bound. So I'll just call this LUB. If that is our LUB, so now we're doing a speculation, and we have alpha here, and it goes now, since, and I'm going to stop at a point and let you guys guess. Now, since alpha is a positive number, I think since alpha is positive, we could subtract it from this guy, and we would still be in the set, right? So we do alpha minus alpha. I mean, lambda minus alpha.
Wait, that takes us, yeah,
That's takes us right here, right?
minus alpha. Oh, yep, yeah.
So we took the least upper bound, subtracted to with our first element, whatever that is, we end up here inside the set A, right? Okay, if this is what we just did, then this thing is an element of this, right? Of the set A. It better be less than. No, this is a element of A. It should be less than the LUB.
Gamma, alpha was.
Lambda. Our LUB. All right. So this should be the case. So this should be the case. So this is not an upper bound, and it is in the set, and then we go. So for some integer, and because this is not an upper bound, UB, for some integer M rather than N, so his intuition was right. We should have this thing. Oh, let's put a number here. here is another number, let's say, this thing, because it's one, this thing here, this is what, an element of set A, should potentially be less than, if we take M and multiply it to alpha, the number that we produce could fall here. Or it could fall after this, right? Is that true? We take some positive integer m, multiply to alpha, and remember the condition is opposite. You multiply anything to alpha, it's going to be it's the opposite of within, right? It's going to be whatever you do, this better be within equal to or less than or equal to beta. Yeah, or in this case, the LUB, right? So it can fall here. It can fall here, right? Before or after this number. This is an element, right, of A. So let's say it fell. That this is the one that we ended up with because of this sum. We chose the right M. If you choose the right M, you're going to generate a element of the set A, which will be bigger than our LUB minus alpha, which is a member of this set.
Okay, so we've generated an element. And if we call that as multiply alpha by that, right there.
This is another N.
Yep.
They could have used N, but it would have been confusing. Okay.
All right, let's do that.
And now what happens is we don't have to do anything. All we have to show is that this number here is all we have to, so remember, in our assumption, this is LUB, right? Yep. We mess with this and get the LUB on the wrong side. And if we get it on the wrong side of the less than, we're screwed, because it should be always on this side. It should be greater than anything here.
You know, it's minus alpha.
Oh, wait, we can add alpha. We just do some algebra.
So we do this. And then what happens? Now our LUB is less than, and this is, then therefore, situation is untenable. This shouldn't have happened. How can lambda, which is an LUB, is smaller than an element of the set?
Wait, how do you know that?
Because, very simple, because I got this wrong. No, I did get it right. So I'm just going to keep the order. Oh, wait a second. So I take alpha out, and I'm going to put alpha on this side, and then this. Yeah, that's fine. That's why it's an element of the set. This is any n.
Oh.
Multiplying with alpha creates the product that belongs in the set according to the definition.
Yep.
And we find out that this element of the set, a real element of the set, is greater than the LUB. That means we've the absurd. We hit the absurd, which means our preliminary assumption that the consequent of the theorem was wrong, and the theorem works.